Excuse me? Yeah. I have no
Okay.
objection.
Welcome, everybody, to the European Non-Associative Algebra Seminar. I'm happy to introduce the speaker of today, Professor Martin Markl from the Czech Academy of Science. The title of his talk is Transfers of Strongly Homotopy Structures as Grothendieck Bifibrations. Please.
Yeah, thank you very much. So, by the way, how long my talk is supposed to be? What is the usual
About
time?
1 hour.
Up to 1 hour. This is fine. Okay, so Dennis, can you move the board so that the people? I mean, there may be some delays due to technique. So this is Denis Bashkirov, by the way, my postdoc who is right now helping me with the camera. So I have probably to say that in my talk I'll be also relying on results or help in general by Markl Rogers from the University of Reno, which is a famous tumbling place in Nevada. And most of the stuff which I'm going to explain can be found on my homepage, written here. Okay. So before I say what are my aims, let me recall some notation. So, all right. So I believe that most people know what A infinity, also called strongly homotopy associative algebra, is. So just to fix the notation, I'll be using the following way to write it. So it has some hardline chain complex AD, and it has some quadratic operation mu2, some higher operation mu3, which is ternary, and so on and so on. And these mu n's are going from a tensor power of a into a, and they have some degrees, but I'll be pretty relaxed about the degrees and signs in my talk. And mu2 is a multiplication which in general needn't be associative, but its deviation from associativity is measured by homotopy mu3, and there are some higher coherence conditions which are measured or whatever by these higher operations. So I believe it's quite well-known notion. So I don't think I believe I don't need to spend any more time on it. If you have any question, just ask me. So there is a quite interesting and rich hierarchy of morphisms. So what is a weak morphism? Weak morphism of A infinity algebras A, D, well, and this flat mu will be my collective notation for all these higher operations. So I'm speaking about morphism from this A infinity algebra into, let's say, some A prime, B prime, and nu prime. Oh, no need for any prime here. So what is it? A morphism is a sequence of maps F1, F2, F3, and so on, where Fn goes from A tensor n into A prime, and what? So F1 is a chain map which is almost homomorphism with respect to the bilinear operation on A and A prime, but not exactly. The deviation from being homomorphism is measured by F2, and there are some higher homotopies which are part of the structure. So there are particle cases. I say that such a morphism is strict if all these higher things are trivial, which means that F1 is not only chain math, but actually a homomorphism with respect of all these higher operations. And this notion is kind of not very important. So we usually use some more subtle notations. We say that such a F is weak isomorphism it's weak isomorphism if F1 is isomorphism, if F1 is isomorphism, and it is some kind of standard exercise to prove that weak isomorphism is actually invertible, and the argument is similar to prove that that Taylor series whose linear part is invertible is itself invertible. And for me, very important notion will be isotopy. So I say that F is an isotopy. If F1 is identity on A, which of course means that actually A prime is A. So this is very, very important special class of weak isomorphism isotopy. So no questions so far? Silence. Yeah. So maybe I can tell you some unprecise history, certainly far from being complete. A-infinity algebras were introduced in topology by Grothendieck in '63, and they introduced the notion of a infinity space and the algebraic counterpart called by Grothendieck A-infinity algebra. But somehow it entered algebra only much later by Kadeshvili's theorem, which I'm going to recall. So then is everything all right? That's a connection. It's very, very strange experience to speak to empty room with absolutely no reaction.
Everything is all right.
Everything is all right, yeah.
Yes.
Kind of ghostly experience, I have to say, but this is the life. All right, so what Kadeshvili proved, and by the way, I have to say that to stay safe, I will assume that all my objects are defined over field. Actually, not necessarily of characteristic 0, but I better want them to be defined over a field. So what about these Kadeshvili's? Kadeshvili theorem, let me call it minimal model theorem. Although I don't think that he used this name. And it says the following thing: suppose that A, D with multiplication is a DG algebra. needless to say that DG algebras are particle cases of A-infinity algebras. Then cadentially proved that there exists a infinity structure on homology. So this is the homology of this algebra. Sorry, of this algebra of this underlying chain complex, and the infinity structure that he existence he proved is of the following form. So differential is 0. Then it has some multiplication, which is actually the same as the multiplication induced on H by multiplication on the original DG algebra. And then it has some high components, and typically they are some high components. And of course, this stated as this statement is trivial because I can do zeros, but it claims that this minimal model, the minimal model, has a read homotopy type of whatever it means of the DG algebra we started from. So this is the existence part, and then he proved that such a thing is unique up to isomorphism. Unique up to isomorphism, and actually I proved in quite recently the stronger version of this minimal model theorem, which says precisely the same thing, except that isomorphism is replaced by isotopy. So the proof is very simple, and you can find it at the homepage of mine, which I mentioned. And I don't want to make much fuss about it because it is indeed kind of observation. I'm only surprised that people didn't notice that before. Okay?
Yes, okay.
Very good. So at least someone is reacting. Very good. So let me move to formal understanding what transfers are. Then if I use this board, will it be visible? Can I use it? Yeah, perfectly fine. So let me state the theorem which actually I proved in 2006, and which is in my opinion the strongest thing which could be proven in this context. So this is a situation. Okay, I'll be drawing something and making some comments. So I got chain complex A prime D prime. I have another chain complex A 2 primes D 2 primes. I got the chain map F1. I got chain map in the other direction G1. And I got a homotopy H1, which is homotopy between what? Between G1 F1 and an identity of A prime. By the way, this theorem holds over any coefficient, so in particle holds for chains in abelian groups. And well, I didn't say what the theorem says. So the theorem says the following thing. suppose that I'm given a infinity structure. I will use the fact that I have colored chalk, so I'm given some a infinity structure which extends this chain complex structure on A prime. Then everything can be extended. Everything extends. By which I mean that, yeah, I may use different color, that there exists an infinity structure nu on this chain complex, that F1 extends to a infinity map, that G1 extends to, again, an infinity map in the other direction, and also homotopy H1 extends into homotopy. Well, I don't have space here, but extends into a infinity homotopy. I didn't even indicate it what the homotopy of a infinity maps is, but it can be done quite easily. And again, you'll find references on my homepage to explicit formulas. So once again, the theorem says that whenever I am given some infinity structure on this chain complex, there exists an infinity structure on the other one, such that everything here extends. F1 extends, G2 extends, and homotopy between G1, F1, and identity on A prime extends as well. Yeah? Camera is out of focus. Yeah. So once again, what is amazing on this statement is that it works over integers as well, and all these yellow things which are on the board are given explicitly. I may also mention the fact, kind of warning, that that some result of this type was proven by Kadeshvili. We already saw his name, and Hipschman. Hipschman in 1991, but these fellows work on the much stronger assumptions. They assume that the following conditions are satisfied. F1 composed with H1 is 0. H1 composed with G1 is 0. And H1 composed with itself is 0. So they prove basically the statement under these conditions, which are sometimes called the side conditions, but they are totally unnecessary, although some people believe that they are necessary. All right?
All right.
Okay,
All
okay.
right, very good. So I move to the next page of my explanation. Maybe I can erase this board. I think this is the one which is the best one to focus on. So maybe I'll erase it. Yeah, there's nothing on the board yet. Yeah. Fine. Okay, so this was on the board, but you cannot see it anymore. It was kind of fine version of this transfer theorem. Let me formulate a crude version of this. So it is saying something about the following situation. Again, I'm given two chain complexes, A prime, D prime, and A prime, D2 prime, and a chain map. Okay, and I'm given also a infinity structure here, mu, fat mu. And the statement is, as you may expect it, that you can expect, okay, sorry, one important assumption is that F1 is chain homotopy equivalence. Chain homotopy equivalence. And okay, so what is the statement? The statement is that if I'm given mu infinity structure on A prime D prime, that F1 can be extended, I use the yellow color, to chain to infinity morphism. And also here, everything extends what I have on board. I have to be more precise. So the theorem says that if F1 is chain homotopy equivalence, then there exists an infinity structure on this chain complex such that F1, which was given, extends into a infinity morphism. And the proof is, well, I mean, it easily follows from the previous theorem, because you can, since F1 is chain homotopy equivalence, you can choose a chain inverse. And then the previous theorem tells you that you have these extensions. Of course, they may very much depend on how you have chosen your homotopy inverse and the homotopy. Anyway, let me introduce the terminology here. Such an infinity structure here is called, or I will call it, or we call it, transfer of mu of this red mu over F1 over chain homotopy equivalence F1. Okay, so what about, as I mentioned, and it's also obvious, the concrete form of mu, and also this extension very much depends on the choices of homotopy inverse and homotopy. So what one may say about such a transfer, let me quote theorem by me and Markl Rogers, which says that the transfer is unique up to isotopy. Let me just draw one diagram here to explain what I mean. That I mean the following thing. So I'm given this, I may draw it immediately, this mu here. I am given F1, chain map F1. I am given it again. I construct some, well, let me change the notation and write it as a BD. And it was yellow. new prime here. And I may also have some other transfer B two primes. The fact that they are transfers means that I have extensions of these chain maps, which may be different. 1 prime, 2 prime. F1 is always the same. F2 prime, F3 prime, and so on. So I have 2 transfers over the same chain map, and the theorem with Markl Rogers says that there exists isotopy E, which is an A-infinity map which starts from the identity of B, and it may have some, and it typically has some higher terms. And remember from the first board that isotopies are invertible, so the implication is that the transfers are unique up to isomorphism, but this statement is much stronger. And in fact, we also prove that such a diagram can be, or that isotopy can be chosen in such a way that this diagram commutes up to A-infinity homotopy. But I don't think I'll need this result in my talk. All right?
Yes.
Red house. Yeah. So, as a corollary of this statement, I get the following functoriality of transfers. So let me again erase the board. Okay, so this is a corollary to this statement of mine and Markl Rogers. So this is corollary. Corollary. Transfers are functorial up to isotopy. Yeah, so I believe that the meaning of this statement is obvious. Let me only draw a diagram which hopefully illustrates this. Okay, so this is the initial situation. I have a diagram of chain maps, chain complexes and chain maps. Well, I use the same notation for differential because differential is kind of always tied to the underlying vector space. So I don't need to introduce any extra notation for it. PD. And here I have a map H1, which is G1 F1. So I have such a commutative diagram. And now I extend it. Again, what I can do, I do the same game. I am given an infinity structure here. So I extend F1 to some A infinity map 2 and so on. Good, so then I have a transfer of mu here. What was my notation? What was notation in my notes? Nu, why not? Nu. Then I do the same trick again. So I extend G1 to A infinity map with some A infinity structure here, which I denote by omega prime, or I do it with H1 with the composition. So I know that there exists some A infinity structure here, let's say omega 2 primes, such that H1 extends to H2 and so on. Yeah. And the statement says that under such a situation, there exists isotopy here that ties these two things together. And moreover, this diagram, the isotopy can be chosen in such a way that this diagram commutes up to a infinity homotopy. And the statement immediately follows from the previous theorem, because both omega prime and omega 2 primes are transfers over H1, because omega prime is transfer over G1 composed with F1, which is the same as H1. And actually, the statement will remain true even if I assume only that these maps here are chain homotopic. Yeah. So now I'm coming to what I've said so far is basically repeating things which you can find in literature. And now I'm coming to the motivation of my work and the main results of this talk. Again, I think I erase it. So, what I've said suggests the following question. Let me put it on the board. So this is the question. We saw that transfers are functorial up to isotopy. So there is a natural question there is the following. Is there a category of isotopy classes of A infinity algebras such that if you interpret transfers as things which land in this category, this fictional category, which the transfers are not functorial up to isotopy, but functorial So I wish to interpret transfers as lifts or whatever of chain maps into some fictional category, such that the lift will be strictly functorial. And actually, the answer is yes, but the construction of this category is surprisingly subtle, and I would need full strength of my results with Markl Rogers. So let me formulate a proposition, and I promise that this is the last kind of technical thing in my talk. So proposition. So this is the input data. F prime is a infinity morphism of A infinity algebra AD mu prime into A infinity algebra B nu prime. I also have another version of this thing, namely F2 prime from some A infinity mu 2 primes into B nu 2 primes, and these are A infinity morphisms, which means that they have some linear part, F1 prime, F2 prime, and so on, and similarly for F2 primes. And the assumptions are that these linear parts are chain homotopy equivalences. So this is a situation. Maybe I can slightly jump ahead and draw a diagram. All right, so this is the diagram. I'll just prepare it and then I explain the statement, but the diagram would hopefully help to understand the meaning of the statement. So I just repeating the input data, A delta U2 primes and F2 primes into B delta mu 2 primes, and here S and T are isotopies. S and T are, but I didn't say what the proposition says. So this diagram is just to help somehow organize the objects which I'm going to mention in now. So the proposition says that the following 3 points or 4 conditions are equivalent. And probably no one will remember it right now, so let me just state them. So the first condition says that these two things, A delta mu prime and A delta mu 2 prime, are isotopic. So this is the first condition I. Maybe I can just try that exists S. The second condition says that there exists isotopy T. The third condition says that there exists T and S. And the last condition, I hope I may lift it so I could write it more easily. There exists T S, such that the diagram D, let's say diagram D, D is homotopic, is okay, commutative. Is commutative up to a infinity homotopy. So this is a proposition, and obviously the last item is the strongest one, but well, actually you have all information to prove if you really feel desperate that each of the others implies it's the last one using the result which I mentioned. Okay?
Okay.
Very good. This is football players or sportsmen doing, like listening to whatever. Fine. So this is it. I may actually leave it on the board and use it later. 4, 5. Okay. So now I erase this again. So now I define the category of A infinity algebras, isotopy classes of A infinity algebras. So this category, I call it, not very surprisingly, isot infinity, and objects are isotopy classes of infinity, and morphisms. So what are morphisms? Morphisms are classes, are equivalence classes of A infinity maps, A infinity maps F A mu. Okay, sorry, it was my notation. A D mu. So the thing which you had on the previous board to be the new. So once again, objects are isotopy classes, and maps of morphism arrows in this category are equivalence classes of infinity maps of this form. And what is the equivalence relation? Now, just for a moment, leave the board. I identify two morphisms of this type if and only if any of these 4 items is satisfied. One, therefore all are satisfied. And actually, you can prove that this is a well-defined category. And I have to say that I spent quite a long time to figure how to define this category and what I need to figure out, what I need to know in order to prove that it is indeed a category. Very good. And the other category is obvious. The other category which I want is obvious. Maybe I use the obvious notation, and this is category whose objects are chain complexes. And morphisms are chain homotopy equivalences. Of chain complexes. And if you believe that there is indeed such a category like isot infinity, you can also believe that there is a forgettable functor that to A infinity algebra associates underlying chain complex. This is quite clear. And to class of maps in isot, the online chain map. So this is again, this is A infinity match. So it has a linear part, quadratic part, and so on and so on. So on maps, it acts by forgetting all these hard things and taking just the linear part, which is a chain map. And well, it was kind of implicit in what I said that if well, actually, this is here. I even assume, or you cannot see that if two morphisms like this belong to the same class, the linear parts are chain homotopic, which means that at least on the first glance it's well defined, and it is indeed a well defined map. Okay. So now I wish to say something like that transfers can be interpreted as a unique lift of something from CEHE into isot infinity, which are functorial. And whenever I'm in such a situation, the gadget that captures is a notion of Grothendieck vibration or Grothendieck op vibration. And actually, I'll need a discrete version. I believe that for most of you, the notion is well known. So let me just very briefly, since I still have 10 minutes and this will be more than enough, recall what discrete Grothendieck vibration is, again, after erasing the board. Some people believe that the notion of a junction and any correspondence between Grothendieck vibrations and resheaths are the two most important results in category theory. I don't know, but anyway, this notion of Grothendieck vibration is very useful. So what is it? I am recalling Grothendieck discrete vibrations. Notion of Grothendieck discrete vibration. I'll mention after I recall this definition why the discrete is here. So, well, it is, first of all, it is a functor. It is a functor from some category E to some category C, and it has the following property. And again, I will use the colors. So I am given morphism F, some morphism F in B, so I'm in B here, and I have a lift. Sorry, I let me denote it a B as a basis, as a base, and I got a lift. The middle in E by the lift, I of course mean that this x twiddle is met by P to X. And under such a situation, so these are given data. Under such a situation, Grothendieck vibration condition requires the existence of unique. Okay, unique, and I use the yellow color. Whose target is a given x twiddle. Okay, so we lift, it means that y twiddle is mapped by P into Y, and F is mapped by P to F twiddle is mapped by P into F. So this is a property of discrete Grothendieck vibration. And if I remove this word discrete, but this will not be important for our for my purpose now, then you'll get instead of uniqueness, you need to require that it is kind of P Cartesian or P Cartesian. I never remember. Yeah, and there is also, and I don't want to spend much time on it. So this is vibration, and if you invert the arrows, mean formally coming to get into opposite categories, you will get the notion of vibration. And notice that we are now in a situation which is very close to what we want. So if as a E I take my iso infinity, if as a D I take my chain homotopy equivalence category, and if as a P I take the forgetful functor, I basically am in the situation which I analyzed in the first part of my talk. So I'm given chain map. Okay, so F1 was it, F1 was it, and I am looking for lift, and I'm given also, well, in this case, I'm given target, so of vibration will be closer to what I was talking. So it's kind of opposite picture, but it works as well. I'm given a infinity algebra here, and I'm looking for a lift of F1 into an infinity morphism, and of course, a lift of chain complex here into an infinity algebra, such that this diagram takes place. And this is practically the end of my talk, because what I claim and what should be kind of obvious why it must be true is that that this delta is Grothendieck discrete of vibration. Of vibration means that it is both vibration and bifibration, sorry, bifibration. Bifibration means that this is both of vibration and vibration. And this is just formulation. The statement is both interesting and dull. It is interesting because it uses some fancy language, and it is dull because it doesn't add any new facts, any new knowledge to the things which I've already formulated. It is just nice way how to pack it. And there is a classical theorem about, again, discrete Grothendieck vibration. Let me just state it classically. There is a 1-to-1 correspondence between discrete Grothendieck, okay, it's understood. Vibrations over category B on one hand, and on the other hand, functors from B to sets. Yeah, and if R is such a functor, the Grothendieck vibration which correspond to this functor is denoted as an integral over B of R, which also makes kind of sense because it's sorry, this is R, because it's indeed resembles integration over fibers. So this is R. Okay, so this is for vibrations over B. You have a similar statement for op vibrations where your functor should be contravariant or vice versa. I don't remember, but this is not important here. But this means that also in my situation, I have such a functors R for vibrations and another functor for cofibrations. And indeed, the functor R assigns to chain complex here the set of all extensions of this chain complex into A-infinity algebras, and similarly for op vibrations. So I can write the ultimate formula of my talk. Maybe I use this board because this will be long. That the category of isotopy classes, which I have just defined, is isomorphic, not even equivalent, isomorphic to the Grothendieck construction of some functor R, which assigns to chain complex isotopy classes of infinite extensions. And it is also, if I think of it as a op vibration, then it is also this Grothendieck construction of some other functor L, which is the same on objects, but morphisms are defined in slightly different way. So we have this beautiful formula, which certainly could be a selling point of my exposition, although, as I say, in effect, it doesn't say anything real deep. It just wraps up the observations and statements which I mentioned. But since it looks indeed very nice, and anyone which sees it would be certainly very fascinated, I'll put it into the yellow box. Okay, so that's it. And I think it's enough for all which I wanted to say. I said, and I wish to thank mainly to Denis Bashkirov, who was sitting here with me, because it's 5 p.m. in Prague, and the institute is completely depopulated, and without Denis, I would probably need to look up for consultation with psychiatrists after this talk. So thanks, Denis. And of course, thank to anyone for listening to me.
Okay, thank you very much for your interesting talk. Are there any questions? Comment? Okay, Friedrich.
Yeah, one question could be, are there natural Grothendieck topologies to put on these categories to make these vibrations or op vibrations into not discrete but continuous functors?
I don't know.
And another question would be
it's very combinatorial thing, so I doubt it, but
okay.
Surprises are possible.
Okay. And another question was, you're only talking about A infinity. Is there some part of the story which generalizes to a general operand or even
this is very good. This is very good question. So why I'm talking about A infinity? Because you have very nice notion of homotopy of A infinity morphisms, and the similarly nice explicit notions you have for let me use this expression for algebras over non-symmetric operands. So, but as far as let's say Lie algebra, so natural question is what you can do for L infinity algebras. Then you are slightly in the trouble because there is nothing like nice explicit formula for homotopy of L infinity algebra. So of things being slightly implicit. I did it for infinity because somehow I wanted to show that such a thing exists on the example, which is explicitly understood, and you can write down the formulas if you want, and I leave it to others to generalize it if they want. The generalization for algebras over non-symmetric operas should be straightforward. The trouble is that I don't know much examples of these kind of algebras which are interesting. And for other things, okay, let someone else takes it up. And do
Yeah, I don't know whether you're aware of it, but there's a rather recent paper by Johan Leray, Eric Hofbeck, and Bruno Valette on transfer for properands. So
yeah, I know of this paper. I know of this paper. I haven't read it, but someday I follow the work of these fellows, and so in principle, I think that you could
would be interesting to mix this into your theory.
But as I say, I leave it to others.
Yeah. Thank you very much.
Oh, you're welcome.
Okay. Any other questions? Okay. If not, let's thank Professor Martin Markl again.
Thank you very much. And I apologize actually for my mistake. I didn't pay attention to time zones, but fortunately the shift was working in good direction, so I wasn't late. I was early. Yeah. Okay. Take care.
Okay. So
thank you.
Thank you. We will resume next Monday at the usual time, taking into account also the change of the time in some countries. Goodbye.
Goodbye.
Ciao.